I have a bit of an unusual job. Companies pay me to find bugs in systems that aren't real. And I don't mean the bugs aren't real. The bugs are very real. The systems, though, they don't exist. All companies are doing is giving me designs of systems they want to build, and I'm supposed to look at those designs and figure out if they're going to lead to really broken systems or possibly good systems. This is a little bit crazy, but it works because a lot of systems, when you boil them down, are very similar, and they have similar kinds of bugs. Let's see this with a simple toy model I call the thing doer. The thing doer runs the do thing routine. And here's how the do thing routine works. Step 1, we check if the thing has already been marked done. Step 2, we mark the thing as done. And step 3, we actually do the thing. Looking at this, do you see a possible design flaw? Yeah, there is a design flaw here, and it's between steps 2 and 3. If we mark the thing as done, and then we crash, even if we retry, we go back to step 1 over there and see, oh wait, I've already marked this thing as done, and we never actually do the thing. Great, this has a flaw. Let's create a new version, which instead does the thing and then marks the thing as done. Does this have a flaw now? It does, but it has a different flaw. It no longer has the problem where we will never actually do the thing. But the flaw it does have, I think, is a tiny bit easier to see if we have 2 thing doers. Then we have do thing 1, check if the thing's marked done, and then it actually does the thing. Before it marks it done, thing doer 2 just comes in and checks if it's done, sees it wasn't marked done, does it again. The thing is done twice. We've now done the thing twice that we only wanted done once, and we have a new bug. This does appear if we have only one thing doer and we do retries, but adding a second one just foreshadows some really fun stuff we can do later. So, who here has written a thing doer? Lots of people have. I have encountered many, many thing doers as a programmer. They are not called thing doers, but they have the same structure. I once worked on a system where, my clicker is having some trouble, that did install app on device. And if you ran 2 of these simultaneously, you would try to install the app twice. That doesn't seem like a big deal, except with this particular system, for some reason, if you tried to install the same app twice, it would just start randomly deleting user data. You could have something like assign speaker to slot, where it tries to put 2 speakers in the same slot, and then we're both on the stage at once just shouting over each other. You could even have something like send package, where you have what happened to my wife once, where she ordered some protein powder and received across 3 weeks 3 separate packages of that protein powder. So yeah, when you get down to it, a lot of implementations, very different code bases, can have a similar intrinsic system behind them. So understanding how that system works can lead to us finding bugs in the real thing. The formalism of this process is called formal specification. There are a lot of tools and languages designed to create an abstract model of a system and find issues in that. We are not covering this. Instead, I want to talk about informal specification, how we can do this entire process without any tools, without any formalisms, just with pencil, paper, and our brains. I think that provides more useful information to more people because you can apply it to any kind of code base at any point without having to lean into learning a new tool set. So really quickly, we're going to cover 3 things in this talk. What does it mean for a system to be correct? How we can manually verify correctness, and the techniques we can use to actually abstract out this thing and make it work essentially. Before I begin, though, I do have a lot of references in this talk, and I think it is very cruel to an audience to force them to write down about 100 URLs at once. So you only need to write down one URL, hillelwayne.com/talk/sd25. It's also on the bottom over there. Just go to this link. I have all of the URLs in one place. Later, I will put up a bit more information about them. I had to rush that out this morning, so. Now, before we can talk about what it means for a system to have bugs, we need some notion of what it means to be correct. The simplest model of correctness is the property model. We say that a property is anything that should be true of a system. If you look at your system and it's not true, then you have to rework your system to make it true. There are a lot of properties that we work with in code. Static type systems enforce properties. The property that max is a function that turns lists of integers into single integers. Static analysis, like Rust's borrow checker, is a property. It is the property that any variable only has one mutable reference at a time. Even things like unit tests count as properties. The test that assert max 1, 2, 3 equals 3 is a property. It is true if the input 1, 2, 3 gives the output 3. We can also talk about properties at a higher level. In our thing doer, we had two. First one, we should do the thing at least once. Do the thing, install the app, schedule the slot, send the package, etc. This is something the system should always do. And we shouldn't do the thing more than once. This is something a system shouldn't do. There are two important notes about properties. The first note is that it is an all or nothing thing. A property is violated if there is a single counterexample that is reachable. Say I look at my conference badge and I see like, oh, it's always backwards. And I propose the property that our conference badges are always backwards no matter what. This needs to hold for every badge everywhere all at once to actually be a property. If I go around and see, Dominic, you violated my property. His is actually facing forward, and I have no idea why. But because his is facing forward, my property is wrong. He has the one counterexample I need. No, this property is not of my system. The second thing that is important about properties is that they're Booleans. They are true and false. And that means we can manipulate them like Booleans. If I say that P and Q is true of a system, I'm saying the system satisfies properties both P and Q. Or alternatively, that P and Q both hold for the system. I can say P or Q to say that P and or Q hold. I can say that not P to mean that the property P does not hold of the system. And that's all the logical connectives used in programming. Formal logic and specification use one more, the implication operator. This is a bit less common in programming, but it roughly means that if P holds, Q is guaranteed to also hold. A high-level example of this is that if I say this food is vegan, it is also by definition a vegetarian. Something being vegan guarantees it's vegetarian too. Does not guarantee it's kosher though. Ask me afterwards why. And this property lets us bootstrap something really, really important. The idea that some properties are mathematically, rigorously stronger than other properties. The definition is a little bit convoluted, so bear with me for 1 minute, but we can say that S is as strong as W if in any possible system, satisfying S guarantees that W is also satisfied for that system. It's easier to see this with concrete examples. If I say, this system has no memory errors, that guarantees also it has no use after free errors. Use after free is weaker than no memory errors. Weaker being defined as S being as strong as W, but W not being as strong as S. Another example is that if I say, for all possible inputs, f of x is greater than 10, this implies the weaker property that we can always pass the output to the square root function and not get an error. At a higher system level, the property of strong consistency, that two data stores are always equivalent in like what they have stored, is a stronger property than eventual consistency. The idea that they can become wrong, they can disagree with each other, but eventually they'll come back to being the same thing. We can even do things like say that a property we cannot automatically verify implies a weaker property we can. For example, we cannot automatically verify that a website is GDPR compliant, but we can automatically verify it has 1 million cookie banners everywhere. Yes. Strong and weak properties are also transitive. If S is stronger than W and W is stronger than X, S is also stronger than X. In the paper, Highly Available Transactions, Virtues and Limitations, Peter Bayless lists various useful properties, consistency models of distributed systems. So he says that any linearizable system is also sequential and causal. Linearizable implies sequential, implies causal. If you want to learn what linearizable, sequential, and causal actually mean, Kyle Kingsbury, who's speaking later today, has a really great site on this at jepsen.io/consistency/models. Again, it's in the notes. If you don't have it now, just go there and you'll see a link there. There is one more consequence of stronger and weaker properties that I find easiest to showcase with visualizations. Let's imagine that we have the space of all possible systems that could ever exist. Some set of those systems satisfy a strong property S. That set will be a subset of the systems that satisfy the weaker property W. Any system in the subset is also in the superset. There are also systems in the superset, but not the subset. And there are systems in neither. There are no systems, though, that are inside S but outside W. In other words, it is impossible to have W fail and S pass. This is what we call the contrapositive. If S implies W, not W implies not S. S holds means W holds, then if W doesn't hold, S doesn't hold either. And this is extraordinarily powerful. Take an integration test. An integration test is more powerful than a set of unit tests. If we know the integration test passes, we know there is some set of unit tests that also will all pass no matter what. We don't even need to run them. We know they're going to pass. On the other hand, by contrapositive, if we know that one of these tests fail, we don't even need to run the integration test. We know it's going to fail too. And imagine we run both sets. We see that this idea that the user buys something with a coupon fails, and this set of unit tests fail. Which of these things, this integration test failing or 6 of these unit tests passing and the 7th failing, gives you more information of where the bug is? Anybody want to point? Left, right? OK, I think everybody's pointed right. Don't see anybody pointing left. What we learn from this is this. Strong properties show that a system is correct. Weak properties show why a system is incorrect. As our work as software developers involves a lot more debugging than writing, we tend to see in almost every verification culture an emphasis on writing a lot more weak properties to verify than strong properties to verify. This is why, for example, in agile testing, the test pyramid suggests writing a few end-to-end tests, then a few more integration tests, then a lot of unit tests. There's a few reasons why they do things that way, but this is one of the reasons. The unit tests provide much more narrow information on what went wrong when something does go wrong. This is also one of the core ideas behind design by contract. If we have the function fill immutable values, we have the implicit property that this is very broadly correct. If we add assertions, then what we've done is said, these failures are, these assertions are weaker properties than the whole function being correct. So if these fail, we have information that the function itself is wrong, but with much more narrow information about why. This example, incidentally, comes from the Tiger Beetle, our sponsor, the hosts of this conference. It comes from their blog post, It Takes Two to Contract, which I believe was written by Alex, who gave the closing speech last night. I've included a link to this again in the notes, as well as some broader stuff about their Tiger style, in particular negative space programming, which uses a lot of these ideas too. The last consequence of weaker properties giving us more narrow information is possibly the most unusual, and the one that makes formal specification possible in the first place. A realistic version of a property running in a realistic system implies the weaker property of it holding in the idealized system. Imagine some system that has the potential to drop messages between various agents, processes working in the system. If there is some property that holds in that real system, there must exist an idealized system where messages are not dropped, not duplicated, not reordered. And in that system, P should also hold. Which means, if we can prove that P is violated in the system that is simpler, that is idealized, that doesn't drop or reorder duplicate messages, we are pretty dang certain it's also not going to hold in the real system that we actually implement. And that's just the entire idea of formal specification. Creating a simplified model and finding bugs in the simplified model leads to us finding actual bugs in the real system if we do build it that way. With that in mind, let's go back to the thing doer. I gave two broken versions of the thing doer. The first one where we check if the thing's marked done, then we mark it as done, then we actually do it. And the version where we swap steps 2 and 3 around. We do it, and then we mark it as done. We know both of these are broken, and we know they break different properties. The second one breaks the property that we don't do the thing more than once, and the first one breaks the property we do it at least once. If I was doing formal specification, I would find a way to formalize both of these systems and formalize the properties, and then use one of the many, many tools and means of checking to check these properties hold for these systems. I would find it doesn't hold, I would find the bug. Again, we're not doing formal specification. We're trying to do it in our heads, which means learning an algorithm we can do in our heads or on paper. There's one algorithm that is particularly suited to that, called brute forcing it. We're going to now brute force model check these two systems. To do that, we start with initial state, a representation of everything that matters to our system. I'm going to say that the initial state consists of 3 things. The step of the algorithm we're on, such as check, whether or not we've marked the thing as done, which is a Boolean, and the number of times that we've actually done it, which is 0. I want to point out that these two first properties, these two first values, step and marked, are internal to the system. They are totally in our control. We can change the algorithm that represents what step we're on, and we can change how we store and manipulate the value of marked. Done, though, done is external. For the most part, we can increment it. We can do the thing. We cannot undo the thing. We have a lot less control over what happens to the number done value. The next step now is we're going to see how the system can evolve. In the happy path, there's only one thing that can happen next. We mark it, we go through the check, we see that marked is false, we go to marked done as the next thing we want to execute. From here, we change marked to true, and then from here, we change number done to 1. I'm going to say that on top of this, we can also do retries. If in this last state we do a retry, we enter a new state, check true 1. From here, if we run the check step, we see it's already been marked done, and we just go back to done true 1. This represents one possible part of what we call the state space, anything that can happen in the system. Next, I'm going to go back and see, is this everything that can happen? Right now, our system is deterministic. Every state has exactly one state that follows from it. I can add non-determinism, saying that one state can lead to more than one possible state. To do that, I will say that exactly one of these steps, this do thing, can fail. It may not actually move to this state. Why it fails is not my concern. Maybe it is because whatever we're doing takes so long that our processes can just crash or enter Windows Update or something like that. Maybe we have some partial chance of failing no matter what. I don't care. All I care is that this might not actually go to here. So it can go to here instead, a retry state, where we try to, again, go back doing check. Except here, we have check and marked true, so we don't actually go to here, we go to here. Done true 0. If I retry from here, I go back here. Everybody understand what's going on right now? Do I need to go into anything in more detail? Okay, sounds good to everybody. And this now represents the whole state space. Every possible state, every possible transition between states. I sometimes find that even if I'm not actually verifying properties, just knowing how to enumerate all the possible states is very valuable to me. But we are trying to verify properties. So let's now see how we do that. Let's start with the one that we know passes for the system. We don't do the thing more than once. This is something bad should not happen. So for that reason, we call it, and what I hope is an obvious name, a safety property. Bad things don't happen. In particular, it's an invariant. It needs to hold for every state, everywhere, all at once. That makes it actually very easy for us to check. We just have to look at it state by state and see, is in this state done greater than 0? is done 2 or more. Nope. In this state, done 2 or more. Nope. This state, nope. This state, nope. This state, this state, this state. Check every state. Every state satisfies their invariant. This is true. Now, what about property 2? We do the thing at least once. This is something that we want to happen, a good thing that should happen no matter what. So for reasons that I hope are not super obvious and actually very complicated and historical, we call this liveness. Ask me afterwards if you want to know why. It's a convoluted history. This is not invariant. It's not true per state. Let's take away all the retries of non-determinism. Is it true in this state that we do things, that we've done the thing at least once? No. This state? No. This state? No. Only in this last state have we actually done the thing. But this simplified version still satisfies this property because the only possible way the program can evolve must pass through the good state. This is what we call a behavior, the timeline, the trace, the sequence of states that the program can evolve through. And liveness properties exist on the set of all possible traces, all possible behaviors. So because there's only one possible behavior here, and it passes through the true state, we know that this microsystem satisfies liveness. This system, though, with the non-determinism and the retries, does not. Because there's a second behavior, this one. In this behavior, it's now impossible for us to ever get to a state where we've done the thing. So for this larger system, liveness does not hold. In other words, to verify properties, we both need to understand all the states and all the transitions between states, all the states and all the behaviors. That's ThingDoer Mark 1 version 0.01. Let's now look at 0.02. Actually do the thing, mark the thing as done. We have a new state space here. These two things swap, these two steps, do thing and mark done. And they lead to new triplets. Do thing false 0, mark done false 1. Then this changes. Because the only step that can fail is do thing, we no longer go to a distinct new step. This now goes back to the original step. Everybody follow that? Okay, cool. Nobody's shouting out, no, this makes no sense. So let's keep going. Does this satisfy liveness? Technically not. And the reason why is because there is actually a trace here, a behavior, that does not ever reach a blue state, green state. It goes like this. First, we check. Then we do thing. Then it crashes and we retry. Then we check. Then we do thing. Then it crashes and we retry. Then we check. Then we do thing. Then it crashes and we retry. Then we check. Then we do thing. Then it crashes and we retry. Then we check. Then we do thing. Then it crashes and we retry. Then we check. Then we do thing. Then it crashes and we retry. I think you get the picture by now. So often when we're sort of like modeling systems, we have to specify that certain things cannot happen an infinite number of times. If we say that you can only crash a finite number of times before you must make progress, then yes, liveness is satisfied in this system. As our last case, let's look at the concurrent system, where instead of one thing doer, we have two. And this gets to, honestly, one of my favorite things about this kind of brute force model checking. How do we represent concurrency? With non-determinism. If we have two distinct processors running do thing, we represent the race condition by just saying that either the first one takes a step or the second one takes a step. Either our red server moves down or our blue server moves right. And we just do that for every single state. If we repeat that, we will eventually find a sequence of states where thing done, where times done is 2 and not 1. This counts as a violation of our invariant, and therefore our safety property, we don't do the thing at more than once, is violated in the concurrent system. That's all there is to brute force model checking. You all know how to do it. Congratulations. Now, there's a reason we tend not to do this super much by hand. And that's because most state spaces aren't 8 states. They're 10 million. So for this reason, we often use tools to do this for us. That would look like first representing the system in some sort of formal notation. This is a pseudocode based on something called pluscal. And I represent saying that there is some parameterization over the number of processes. We have a process called a thing doer. It's allowed to retry. It has a certain number of processes that I can change per model check. Then it has 3 distinct steps: check, do, mark. And do is non-deterministically either increments done or it fails. Most notations support this ability to represent parameterization and non-determinism. That's basically the core things you need over like a programming language. Then we'd have some way of representing the properties, such as saying that safety is always done as less than 2, while the liveness is eventually is done as greater than 0. The actual specifics of what this notation will look like and the semantics depends on the language you're using, but it's all the same idea in the end. Create an abstraction of the system, create the properties, check them against each other. Even so, even if like you can't do a full like 10 million state system by hand, I think being able to do it for a few states is useful. Often when you sort of develop like the specification eyes, you're not sort of looking at like, okay, how can this entire system evolve and does it break by property? You're looking at the design, you see like one small subsection, and you're like, that doesn't look right. And then you sit down and you draw out the lines and the diagrams and the arrows, and you go like, okay, I've now sketched this out and I see that yes, there is a race condition that does lead to this property being violated. That ends up just being a very useful skill that I use like ad hoc all the time. But regardless of whether you're using a tool or you're using a skill, the key thing you need to be able to do is figure out the simple system from either a design or a large, complicated implementation of code. And the question of how do we find the simplifications, find this essence, is called abstraction. How do we abstract out the core idea from the complicated system? This isn't really something I can just explain to you how to do. Like any other skill, it's something that takes practice. I watched Andrew Kelly's talk earlier, and it was amazing, but I still don't know how to actually like do I/O and interfaces and stuff like that. I'm going to have to actually practice it. So, but I can tell you some of like the techniques that you start to develop over time. The first, very important, is the grain of atomicity. Trying to figure out where race conditions can happen and where race conditions can happen and where we assume that things happen so fast or so close together or in a transaction that nothing can interrupt them or fail part way. So in our case, for our thing doer, we assumed that all 3 of these were atomic. We had the possibility of something else happening or a race condition in between step 1 and step 2 or step 2 and step 3. I would get a very different system if I said that 2 and 3 were atomic and happened simultaneously, or if we said that 1 and 2 were atomic and happened simultaneously. Maybe this would remove the bug. Maybe it would leave something missing on the table. Maybe it would just lead to a simpler system, but the same kinds of bugs. It's something I'd have to sort of see and test out to sort of feel. The second heuristic that we often use is to reduce fidelity. In a real system, how do you actually mark something as done? My immediate thought goes to, okay, I probably have a database, and in the database there'd be a row, and the row would have a completed at column, and the completed at column would have a date time, and if that's null, then it's not done yet, and if it's actually a timestamp, then it's probably done. But for the high-level model, I don't need any of that. I can just say it's true or false. One client I worked with recently, actually, they were trying to model something involving server loads, and they represented the load on server as a number from 0 to 100. And they said that the server was overloaded if the server was over 80% utilization. They had a really hard time trying to like specify everything that was going on in their model and see where the bugs were. But then we replaced it, instead of it being from 0 to 100, just a true or false. Below 80, above 80. And once we did that and did the simplifications with that, it led to the bugs being much more obvious. So reducing fidelity is probably the core technique that you will be using all the time to find bugs in these simpler designs. The last technique is a bit more advanced, but honestly my favorite, and part of the reason I wrote this talk was so I could just talk about this one concept. This idea of non-determinism. Non-determinism is actually a simplification of deterministic processes. You got all that? You got it all internalized? Makes perfect sense to everybody? Okay. So you might be surprised, but you've actually used this yourself. Because, show of hands, who here has used a rand in any program you've ever written? Okay, that's most of you. Do you know how your rand works? Cool, awesome. Okay. But Rand is, for the most part, in most cases, a pseudorandom number generator. It follows a deterministic algorithm that takes a seed and produces a next seed and a next value. One possible way to generate the next value is proposed in the C11 standard guide, and it's this. Take your global state, multiply it by 1,103,515,245, add 12,345, and modulo by 2 to the 32. So how many people, when you're sort of writing your program, are just like, I'm calling rand? I definitely know the next value is going to be taking the current value, multiplying by 1,103,515,245, and adding 12345 and modulating by 232. Do you do that? Anybody? OK, you might actually do that if you're working with like low-level cryptographic primitives, where it's really important to understand how exactly your RNG is working. But if you're working at a higher level, it is much easier to understand the program by abstracting out what the PRNG is actually doing and just thinking about it as some sort of non-deterministic selection from a set of possible values. Similarly, when modeling, we do the same thing a lot. I could have some really complicated deterministic code which checks a lot of different choice points to return one of two values or throws an error. But I can remove all that determinism, all that complexity in the abstract model by just saying, well, it either returns X, or it returns Y, or it fails non-deterministically. This is a thing that I find people have a lot of trouble getting used to. But once you get used to it, it just opens up so much power and so much flexibility in modeling. So that was a lot of stuff. Very, very dense. Let's go through a quick summary. Systems have properties. Some properties are stronger than others. You want strong properties to show correctness of a system, and weak properties to show incorrectness of a system. We can learn useful information about systems by looking at their simplified models. We can understand a model by examining the whole state space, which we can do by hand or in our heads via brute force. We can also use tools to do this for us if the state space is too big. And finally, one of the key techniques in doing this well is abstraction, including understanding atomicity, fidelity, and non-determinism. There's a lot here, I know. So I'd like to actually leave this off by showing where you can learn more about this. This is a high-level overview, but there is so much to each of these ideas, and we can go so deep into any one of these. And I will if you let me talk about it afterwards. But if you don't want to find me afterwards, I'm going to recommend a few resources. If you look at this and gone, wow, this all comes from formal specification. This sounds awesome. I want to use this too. Well, there's a lot of tools out there. The one that I end up getting paid the most to use, so I'm the most partial to for that reason, is called TLA+, which is a decent mix of power, expressiveness, and tooling support. I've actually written a totally free online book called Learn TLA Plus on this link that you can go to. And it covers basically everything about how to use it. It also covers topics like making it run faster, understanding all the tooling, how to represent complicated systems. Or if you want to learn more but faster, just hire me to teach you or consult with you. That also works. Second best choice. Additionally, I just do need to mention that formal specification, this thing that we've been talking about, is actually a subset of the broader field of formal methods. Formal methods being anything about proving code correct. So not just that the abstract system works, but that the code you're writing also works correctly. I have less to recommend on this, but I do maintain a website called Let's Prove LeftPad, where you can compare and contrast how you prove code in a lot of different formalisms. And I do need to say that even if any of the things I recommend to you don't work, I'm happy to talk to you afterwards to find something that does. There's a lot of tools in this space, and I respect most of them, if not all of them. And there's not really any holy wars here. It's not like Vim versus Emacs, Vim. I will help you find what you need. And on the other hand, if you heard this talk and you're like, wow, that seems really cool, I don't think I need formal specification, but I really like the ideas. I'm working on a second book called Logic for Programmers. It covers all the ways that learning logic can help you write software better. And it's really, really focused on applications. Things like how logic helps you refactor, how it helps you write better tests, how you can analyze database queries and invariants using logic. It's right now available as a PDF. I'm still iterating on it. I've released about 11 versions right now, and I'm hoping to have a final version ready by the end of the year, and that will hopefully be put into print. If you buy it now, I'm making it a lot cheaper, and you just get all the PDFs in the future if you do buy it. Final thing I want to say is that this talk was fundamentally an experiment. I've been doing formal methods for almost 10 years now professionally, and there's just so many really cool ideas in it. But it's also so niche that most programmers haven't heard of it, much less learn these ideas. So I've always been a little bit obsessed with trying to figure out what ideas I can sort of pull out and teach to other people so those new concepts are useful for them directly without them having to learn the rest of formal methods that comes along with it. Giving them the banana, not the whole jungle and the banana. So this was just a few of the ideas I thought could be handy to everybody here. And if they are, I really want to know. I want to know what happens if in a couple weeks you just try to think about these ideas and try to use them. I want to know if it worked for you, and I also really want to know if it didn't work for you, if I should be focusing on other things that might be more useful instead. So please, just find me and let me know if any of this stuff ended up helping or not helping in any way. And with that, that's all I have to say. Happy to answer any questions.
Thank you.